Welcome back to After Lunch, where I'm taking you back to school. So I expect everyone's complete attention for this entire talk. There may be questions. I don't know. I'm just the guy that put this together. And I do want to say, Yvonne, I know you said something about 100 slides. You know, Bill and I were just talking. That's usually what I have. Don't worry, it's still over a gig. So it's still a very large presentation. But we're going to talk about RGB usage at the National Weather Service Ocean Prediction Center. And if things go right, I'm going to start off with this slide just to show you, this is today's map. How busy can we get? Well, we have a tropical storm out here in the West Pacific that's being monitored by the Joint Typhoon Warning Center, a hurricane force low in the Gulf of Alaska, and a complex storm force low in the northwest part of our area of responsibility with a very long cold front with very strong winds through that whole area. Just so you know, when a tropical cyclone gets north of 30 in the Pacific, we are responsible for writing up the tropical forecasts, taking JTWC's inputs. So now our text products get very long. So this forecaster today walked into quite a bear of a weather pattern. And this is only October. It does not get better from here, not for the next few months. So when it comes to RGB usage, and I think we're hiding some of my slide. Thank you. Here's how I kind of laid it out. I'm probably missing some things, but surface analysis, largely using air mass, geocolor, nighttime microphysics. We have incorporated some of the proxy viz recently as well. Storm force versus hurricane force diagnostics using air mass, geocolor, extratropical and tropical transitions. When the Hurricane Center is done or the Joint Typhoon Warning Center is done with the system, we take responsibility for it. When do you make those decisions? We're finding that air mass RGB in particular is pretty helpful for that. Fog analysis, nighttime microphysics, day snow fog, geocolor. Marine convection, that's something that's a little bit newer. We're still kind of playing around in the sandbox with that. But some of the convective ones that have already been discussed, I'm looking into, and dust diagnostics, specifically for the Saharan air layer. It does bump up to 31 degrees north, which is our boundary with the Hurricane Center. So we do have to pay attention to it. I don't know why does it keep doing, oh, here we go. There we go, I got it. Okay, so like I said, we're going back to school here. So typically putting together a service analysis, you have the previous map as far as features underlaid. We'll put some spaghetti diagrams, if you will, multiple models on one screen, trying to figure out if there's consensus at our initialization points. And we start to plop our lows and highs. Yes, I used the word plop in the presentation to designate where those areas are. And then we'll use other model fields to start to draw out again, where the highs and lows are, but how are your moisture convergence and your thermal convergence setting up. Then we'll start pulling up some of the satellite imagery. In this case, the air mass RGB is pretty useful as combining the 7.3 and 6.2 water vapor channels. You're able to see some of these features get highlighted a little bit better, sometimes better, not all the time. Than the single channel, but it's also good for a quick look when you're trying to match it up with the infrared. Then from there, in this case, I pulled up the Himawari geocolor, thanks to Steve Miller's work on getting that to us. And again, we're now adjusting the preliminary highs and lows. This is just a quick, I pulled the 0.86. We find that to be pretty useful in the daytime for the ocean areas. Again, matching up features in the Eastern Pacific. And I really think this is a slide that can say 1,000 words if I just be quiet for the rest of the time. How many OBS do you see there? We don't really get a lot of OBS. It's not a luxury for anyone doing marine forecasting. Satellite winds up being our most heavily used tool in this case, but we still use whatever OBS are available from ships, buoys, as well as nearby land areas to just kind of adjust features as we move along. So again, going back to the satellite imagery, we then pull in ASCAT. ASCAT, I think, is a huge lifesaver for us. In this case, I'm going to go back and forth a little bit. If you look on here, look at where I have this 1012 low. Notice I have a couple lows back here in the Southwest Pacific. Nothing in this area, but based on the imagery, based on the ASCAT imagery that is, I'm making adjustments, but also you can see the biggest jump to the Northeast. Now you may say, well, okay, this is a map. Okay, we're looking at 0Z ASCAT imagery for a 6Z map. So I have to then, in my mind, extrapolate that forward because I don't have additional ASCAT for a few more hours. All right. But it winds up being a big help when you're trying to adjust features where they should be, as well as whatever satellite imagery is available at that time. Again, we can go back to the imagery and you can see how things have changed from just a few spotty lows in this baroclinic zone to then all of a sudden you're getting lows popping up all over the place. And then finally, we finish. Now, this is going to be your first question of the day. I'll see how many I get to ask. We then finish up using 925 millibar vorticity as well as temperature advection. Does anyone in the room or even online want to guess why over the oceans we would use 925 as opposed to a 10-meter temperature advection? Any guesses? Don't be shy. You're getting in the right area. We heard wave height. Think of SST temperatures. That gets washed out in the models. It becomes unusable. So 925 is our next best guess. Most of the times of year, especially in the winter cool months, it winds up being a pretty good fit. In the warm months, you can have some bit of offset, and then the forecast has to adjust. And then we finally piece it all together, and all this happens in 30 minutes. And then we have to send it to the Weather Prediction Center so that they can clip and attach things. We continue to work, and then we'll eventually send the map to the Hurricane Center. There's a lot of moving parts. It's not as easy as just putting down your highs, lows, fronts, trough features. Then we have to adjust isobars. It's a very hands-on, very long, laboring process. But for people like me, I actually find it fun. Maybe not everybody shares that, but I do. So now I'm going to go to, okay, we've done the surface analysis. Now we need to look into, what surprises may exist that were not caught on a previous map. So I'm going to start with this. I have ASCAT overlaid for this particular case. We are looking in this zone up here, capturing the Kamchatka Peninsula, all the way up along the coast of Siberia, towards about the Bering Straits up here. And if I zoom in, if it works, there we go. You'll see that I have a sub-gale based on the winds, about 25, 30 knot winds here. So the forecaster at this time, sorry, I think I have too many things. This is where 1.2 gigabytes hurts. In this particular map, you'll see we have no gale and no forecast of a gale. There's no 24-hour point showing a gale might exist because there was nothing in the guidance. These little polar lows that like to ride along the Siberian coast can be a big challenge for us. Then I come on shift and whoops. Now we have gale force winds, and this is not over ice, this is over water. That's a problem. So I had to adjust. This system's pretty well forecasted, the models capture it pretty well. So here you see, this is actually in the cold conveyor belt part of the system. And I'm going to tell you why that's important. Because when you look at the satellite imagery, you'll see that there's two lows. Here's one. Another one forms to the lee of Kamchatka. Here's what becomes our gale, but what we typically would look for to diagnose the gale versus storm force or subgale was not very helpful in this case. This is actually a null case. I know I'm showing something that didn't work, and the air mass imagery in this particular case was not as helpful. ASCAT wound up being our most useful tool, and there are not enough observations up there, especially in March. That's a pretty violent area, but these little lows can lead to very big problems in our forecast operations. But how about a storm force and hurricane force extratropical cyclones from last October? So I'm going to play this through maybe once or twice. I don't even know where to tell you where to focus your eyes. There's a lot going on in this particular case here. I could ask another question, but just for fun. This is just for me. Anyone want to guess which one of these became the hurricane force low? If I had money, I'd give you money if you get it right. Yes, there's the imaginary money. So in this very active pattern, you also have a very strong Bering Sea system, but you have a very active pattern with a pretty warm East Pacific at this time. And this became a very strong, I believe it was over 70 knot hurricane force low. So the first two images I was going to show, here's our surface analysis overlaid on air mass RGB. We did not have ASCAT yet. We had some model data as well as the imagery to use, and based on recognition, the forecaster at this time did put storm force winds, and then it was confirmed later on, a few hours later actually, with ASCAT. So pretty good job there, a way we're able to use the imagery to get ahead of and determine whether or not we can actually trust the imagery. Here's another one. I'm not giving you the hurricane force in this case. This was a surprise storm force. Model guidance was not very good in showing us how strong this system would get as it approached British Columbia. But as it did approach, it wrapped up very tightly. The models then quickly jumped on it. Of course, nothing like getting a 12-hour, 6-hour forecast saying, oh, hey, by the way, that one's a storm force. So forecaster attached it. We wound up getting a ASCAT pass a couple hours later. There's your storm force winds. So these were success stories in how we were able to utilize the imagery with the model guidance to make a decision. Again, you don't want ships anywhere near this. So God forbid there's a ship there and it gave us an observation, yay, we got 50 knots, but that ship is not happy. And further, they're probably not happy with us. So I don't want to take that phone call. So extratropical to tropical transition, something we don't talk as much about. We like to talk about the inverse, tropical to extratropical transition. This is a case where at the beginning of the storm, OPC is issuing warnings, gale warnings, and then it winds up going through a subtropical phase and tropical storm phase. At the moment it becomes subtropical, the National Hurricane Center takes it over. It's well in our waters, but it has tropical entities, therefore they take over all responsibility for that particular storm until it winds up becoming extratropical again, which does not happen. Here it becomes a remnant low, and then the Ocean Prediction Center takes it back over. Here's again air mass imagery. Yes, very air mass heavy today. Final question of my presentation. Anyone want to guess if that's Joyce, what hurricane is that? You'd really have to know your 2018 season, so I'm not going to blame anybody. I'll actually be very impressed if you get it. No one remembers the innocuous storms, right? It didn't hit any land. No, it begins with H. No. This is Helene. So while Helene was ongoing in the far eastern Atlantic, Joyce formed, and there were two other storms in the western part of the basin. So a very active period, but it goes to show, you know, after Joyce starts following Helene on the way out, it gets left behind, trapped under a ridge. And then it's really interesting how you can then follow how the upper level, this is a brand new tropical upper tropospheric trough that then sort of tries to couple with the remnants, but it could never really initiate again because of these subsidence. All right, come on. And finally, this is my final slide here. We do use the nighttime microphysics pretty heavily for fog. I'm trying to get others to use the day snow fog during the daytime. Geocolor also very helpful in the daytime. In this particular case, we've talked a little bit today, this morning about ocean color, ocean products, things of that sort. I think you could probably agree it's pretty easy to see the Gulf Stream highlighted pretty readily down here, the north wall very prominent. Then you have this eddy up here, and notice how the fog, you have the more opaque, I'd call it kind of a turquoise, whitish cloud cover, is most likely stratus cloud. To the north of that, over the cooler waters, is more of a sea fog. And if you watch enough of these events happen, you can actually see how you can tell the difference from fog versus stratus. By the way, fog almost seems to dance or glide across water much easier, while the lower level clouds become a little more more affected by the steering currents at that particular level. So the Georges Bank area, which sits right about here to the southeast of New England, is a known fog area. And we're really trying to highlight with the forecasters how to better identify what is fog, what is not. Mariners care a lot about fog, as I'm sure you can imagine. So with that, my final animation, this is a full winter's worth of storms. I wanted to give the Atlantic some press because we focus so much on the Pacific, but I'll take any questions if we have some time.
Thanks for your presentation, Michael. In the US, we got some difficult choices to make with GeoXL, our band selection. One of the things that I've had our students do is look into whether we really need the ozone band.
Mm-hmm.
I know it's part of the Air Mass RGB, but my question is, can you get how much of this information that's in this Air Mass RGB can be replicated just by using the water vapor bands, the IR window? Is it possible that we should be innovating another RGB for synoptic purposes? Because I never heard anybody say, you know, we can see these features just in the ozone channel.
Right. Okay, I'll agree with that. What this really comes down to is the product is giving you an overlay of water vapor features on top of features caught in the infrared. All right. Yeah, you could look at them separately. You'd be asking the forecaster to toggle back and forth between screens if you can't find a creative way to put these together into a full, like, masked or a combined product rather. The ozone part where it comes out is in the red colorization, the blue colorization, in those areas where you're getting much more interaction with the high latitudes versus mid and then low latitudes. I honestly don't know how to answer your question because it's hard for me to now think of taking that one band out if it's not available, and think of another way that after all these years of working with forecasters to better identify some of these features, again, in that combined product, they now know how to identify. I'm not speaking just for myself. This is across the board at the Ocean Prediction Center and in a lot of the National Hurricane Center. So there would have to be a creative way to give you a product similar to this where you can see that interaction occur in one screen and not ask the forecaster to take more time out of what can be a pretty busy analysis or forecast process. I don't know if that answers it well, but it's the best I can think of right now.
Yeah, just maybe an answer. I remember our former colleague Jose Prieto coming to me one day and saying, "Oh, I'm not very convinced about this Air Mass RGB," and he was actually saying that, and there is a case, I have to dig it, where he was trying to prove that only the water vapor channels were enough to replicate very similar thing like that. That's one thing. And another comment is, I'm surprised you didn't fine tune this RGB for your needs, especially with this gale force, small, low. And along that comment, sometimes I find single channels 0.6 or 0.7 more useful than Air Mass RGB, locking down to some features and topography of the moisture.
All right, I'll give the one comment on fine tuning. Unfortunately, this is coming from a gem pack based NA width where we do not have that luxury that you're talking about, but we would love to be able to play with that one day.
Yeah, not all the weather service has the same display technology. We can have a separate discussion on that.
That's also why this is a little grainier.
So I'm going to partly answer Jordan's question. We did a couple studies looking at the differential water vapor compared to the air mass, and you couldn't see the extent of the stratospheric intrusion as well in the differential water vapor, which only uses the water vapor channels, but you can see the depth, which you lack the depth from the air mass. Okay, so maybe some of that will come across.